In this talk, I'm going to give a high-level overview of the HPCToolkit performance tools. Rice University's HPCToolkit performance tools are designed to help you measure and analyze the performance of CPU and GPU accelerated applications. I want to mention that we're not affiliated with IBM's HPCToolkit or the Intel OneAPI HPCToolkit. We chose the name HPCToolkit 20 years ago before either Intel or IBM started using it. So HPCToolkit was designed to be easy to use. You can profile unmodified application binaries. It is fast. There's low overhead measurement. When you're measuring an application on CPUs, generally the overhead is just a few percent. For GPU accelerated applications, the overhead will be more if you're making frequent calls to the GPU APIs, and that's just a function of the GPU API monitoring. HPCToolkit is supposed to generate informative data to help you understand where an application spends its time and why. So we provide call path profiles that associate metrics with application source code contexts. In particular, we're associating metrics with call chains, where a call chain includes a chain of procedure calls. And it also includes things like inline functions, templates, loops, and statements. Optionally, with HPCToolkit, you can collect traces as well to understand the execution dynamics of an application. We've designed HPCToolkit to be accessible to a broad audience, including application developers, framework developers, runtime library developers, and tool developers. Let's look at what HPCToolkit does. It employs binary level measurement and analysis. This enables you to observe executions of fully optimized, statically linked or dynamically linked applications. Typically, applications are dynamically linked, which means that at runtime, in addition to the application, it loads shared libraries as the application executes. HPCToolkit can support multilingual codes that are any mix of C, C++, or Fortran, or any language that's compiled to native machine code, including binary-only libraries that are potentially dynamically loaded at runtime. So HPCToolkit measures CPU activity using sampling. The advantage of sampling is it has controllable overhead, and it minimizes systematic error and avoids blind spots. So if you were just using source-based instrumentation and you instrumented your application, then you might miss all of the shared libraries that are loaded into the address space as the program executes. Sampling, we sample everywhere, and so we don't have any blind spots. So HPCToolkit enables data collection for large-scale parallelism because we can collect compact profiles, and the profiles will reach a fixed point in size, and so we can collect profiles for lots of threads or processes on a large-scale system. So HPCToolkit, in addition to measuring the CPU, can measure the GPU as well. And to do so, it either uses function wrapping, where we're wrapping functions in the GPU API, or if we have CUDA or HIP, the tracing frameworks provided by AMD and NVIDIA provide callbacks that enable us to monitor GPU operations. So unlike sampling, where we can control the frequency, the callbacks for monitoring GPU operations occur with the frequency at which GPU operations are called. And so we can't control the overhead there. It depends on how frequently the operations are called. So as an application executes, then a monitoring thread is recording information about asynchronous operations that execute on GPU devices. So HPCToolkit will associate metrics with both static and dynamic contexts. On the previous slide, I mentioned that we're associating things with calling context. And so the calling context can include loop nest procedures, inline code, and the calling context span both CPU and GPU on some of the platforms. So HPCToolkit's user interfaces enable you to compute derived CPU and GPU performance metrics of your choosing. You can compute formulas, you can specify formulas that will compute metrics based on the data that you've collected. And this is useful because diagnosis of performance problems often requires more than one species of metric. For instance, it doesn't do much good to know how many cache misses occurred, but if I know how many cache accesses there were and how many of them missed, then I can compute a miss rate, and that's more meaningful than just an absolute number of accesses. So HPCToolkit also supports top-down performance analysis, which enables you to identify costs that are of interest and then drill down to the root causes by looking up and down call chains or looking at the execution over time. This slide shows HPCToolkit's workflow for CPU applications. There are 4 basic tools in HPCToolkit. There's HPC run for collecting profile information as an application executes. There's HPC struct for analyzing binaries. There's HPC prof and HPC prof MPI for interpreting profile data. And then there's an HPC viewer user interface. And so I'll go through each of these in just a moment. To adapt this for GPU accelerated applications, we only made a simple change. We're using the same 4 key utilities, and the only change is that GPU binaries are recorded as an application executes. So if as an application executes, the application JIT compiles a GPU binary to tailor it for the GPU device that it's using, then we record the binary that was generated on the fly. So now let me go through the workflow in a little bit more detail and show you how the whole thing works. The first step of the process is to compile your source files into an optimized binary as you normally would. So one of the things that you might like to do is to add -G to the host compiler as an argument. It's not strictly necessary in order to collect information with HPCToolkit, but without -G, HPCToolkit can't map your measurements back to anything at a finer grain than an enclosing function. And so if you want your performance costs mapped back to individual source lines, you need to direct the compiler to or record line map information as it compiles the code. And so that's done with the -G option for the host compiler. For GPU compilers, there's often other arguments that you might need to provide, such as -line-info for NVIDIA compilers. The second step in the workflow is to use HPC run as a launch script to launch your application and measure it as it executes. So HPC run, we use sampling to collect profiles on the CPU. It will use an interception of the GPU APIs to intercept the GPU operations and monitor them as they execute. And so in addition to the profiles, we can collect trace files as well. And the traces are different than you would get with other tracing tools. For the CPU operations, we're getting traces of samples. And for the GPU operations, we're getting traces of operations as they execute on the GPU. The third step of the workflow is to use HPC struct to analyze CPU and GPU binaries to recover program structure. So by program structure, I mean functions, also inline code, information about loop nests that are contained inside the procedures, as well as the source lines. So the information about the source lines and the inline functions comes from information that's recorded by the compiler, and information about loops is recovered by analyzing the machine code and determining what the pattern of jumps is and interpreting it as loop nests. So the next step is to use HPC prof or HPC prof MPI to take your profiles and traces that were recorded and use the program structure information that was generated by HPC struct to interpret the profile and trace data. So we're going to correlate the information in the profiles to the static and dynamic program structure. Static program structure like procedures and loop nests, and dynamic program structure meaning call chains. And then finally, the last step is to use the HPC viewer user interface to present the trace view and the profile view, depending upon the information that you've collected during the measurement phase. So this shows the code-centric view in HPC viewer. And so it's showing us in 3 panes. We have the source pane, the navigation pane, and the metric pane. The metric pane is whatever metrics we decided to record. And then there's a couple of controls. There's view controls. So what we have is a top-down view, a bottom-up view, and a flat view of the calling context behavior in your application. And then there's some controls for the metric display that allow us to select hot paths, to compute derived metrics, to select what metric columns are to be shown, and finally to output this frame in CSV format so that you can analyze the data with a spreadsheet. So one thing to note is that in this view, we're showing a top-down view of a call chain. And the call chain here includes not only the function calls in their full calling context, but the different colors also show that there's inline procedures, inline templates, outlined OpenMP loops, and loops that were present in the original program. And so when we're measuring things with HPC run, we're recording things at runtime about the dynamic call chains. And then with HPC struct, we recover information about inline procedures and inline templates and loop nests. And then we overlay that on top of the program structure to get these rich call chains that enable us to interpret the information. This slide shows HPC View's trace view. This trace view enables you to gain some insight into how an application executes over time. On the vertical axis, we have threads and MPI ranks, and on the horizontal axis, we have time. And in the main pane here, we see colors, and each color corresponds to a procedure that is being executed by a particular thread or MPI rank at a particular point in time. And on the right-hand side, we see a call stack, and that call stack corresponds to the location where the cursor is shown in the middle of the display. And that shows the call stack that's associated with rank 93 at 86 seconds into the execution. And so in the bottom right corner, we see a menu map, and that shows us the fraction of the execution that we're displaying here. So this is actually a 256 rank execution of an adaptive mesh refinement code that computes astrophysical flashes. I'll go into a bit more detail how to actually collect information and analyze code performance using the utilities that I just described. And so to conclude this brief introduction, I just want to point you to a few things. So there's a project website, HPCToolkit.org. On the website, we have some documentation, including a detailed user manual. There are instructions on how to install HPCToolkit and its dependencies on systems of interest to you, perhaps a desktop or a cluster. There are also some longer format tutorials that go into the mechanics of using HPCToolkit's tools in a bit more detail than I'll have time for today. And if you have any questions, problems, or bug reports, you can always contact us at hpctoolkitforum@rice.edu.